Oh, can we even see? Oh, I see. Our slides are presented conveniently.
The thing.
That's probably right.
So, yeah. Hello. I'm Julian. I'm the processing tools lead for the analytics infrastructure team at Twitter. And here's Nong. He's a software engineer at Cloudera working on Impala. And we're going to talk about Parquet, columnar file format for Hadoop. So to give you an idea of what we're going to talk about, first, we're going to share some context of how we got to develop Parquet and why. And then we're going to share some earlier results from several companies on what we see in performance and compression. And then we'll go in a deep dive and talking about the format and how it works. So first, the Twitter context. So Twitter has a lot of data. We have over 200 million users, monthly unique active users, and that interact and produce over 400 million tweets a day. So that produces hundreds of terabytes of compressed data a day. So that's a lot of data. And storing and analyzing this data is a big deal. So our scale is huge. And so the analytics infrastructure team that you have in an illustration here is in charge of trying to make that easy and scalable. So Twitter's use case gave you here an example of one of our big schemas. So we use Thrift to store logs, and Thrift lets you describe structures and how you store your data. So here's an example, and it's pretty big. It has 87 columns and up to 7 levels of nesting. So that represents one of our real-world use case of how we store data on HDFS, and it's deeply nested. And for example, you can see you have things like IP address, event type, and if you'd want to do a query where you want to count how many distinct event types per IP address, you really need to access only those 2 columns out of 87. And that's where a columnar file format is going to be helpful, because that way you need to load only those 2 columns to do the analysis. So the goal of Parquet is to have a state-of-the-art columnar storage across the Hadoop ecosystem. So it's really to enable the advantage of columnar format in any framework, whether it's Pig or Hive or Cascading or Impala, without tying to one in particular, to take advantage of the columnar storage in existing frameworks like Pig or Hive, while also enabling more efficient execution engine like Impala. And now I will let Nong talk about the columnar storage.
Yeah, so the benefits of a columnar storage for data processing has been well studied in the literature, particularly in the database space. The key benefit is that you take your data, and instead of storing it row major, where an entire row is contiguous on disk, you first take all of your rows and split it out by column. So all of the values for column 1 come first, then column 2, then column 3, and so on. And this gives you numerous benefits. It's very typical in our customer workloads to have tables that are very wide. Say Julian's use case had about 90 columns, and we see that very commonly. But queries only usually touch a fraction of them. You have a 90-column table, you might touch 10 of them. With a row store, you're forced to do all of the I/O for that entire table, even though most of the data is not necessary. With a columnar store, you would only read the 9 columns off disk that your query needs. So that is a huge reduction in I/O and the associated performance gain. The second is that now that you have split your data into homogeneous types and values, you can take better advantage of compression. So you can imagine how now that all of your int values are stored together, that gives you opportunity for better compression than something generic like gzip or whatnot. You can have a type-specific encoding. And then lastly, the data is now not only homogeneous in type, but content. So if this column was people's first names, that would have a very low cardinality. So you can do even better than if it was just generic strings. And then the columnar storage also gives opportunity for much more optimized execution engines. So the latest versions of x86 hardware has SIMD instructions that way you do the same instruction on multiple data values in one cycle, and columnar storage makes that much easier. So we have been working with Twitter on this format for a few months now. We started last fall. And at the time, we were looking to build a columnar store for Impala, and we knew that they were working on a similar problem for their stack. And we realized that if we combined forces, we would have a much better chance of coming up with something that was language independent and formally specified and would work across most of the, or more components of the Hadoop stack. So currently, it's 100% open source Apache license. You can find it on our public GitHub, where we formally define the spec as well as the various implementations. So here are some initial results based on the Impala code base. So in this case, I've taken a well-known benchmark data set, the TPCH data set, and I've taken one of the tables of it, in this case, the line item table, and this is at the 1 terabyte scale factor. So for this case, the line item table raw is 750 gigabytes, as you see in the column on the far left. The other columns represent different file formats that Impala currently supports. So we have text with LZO compression, and then sequence, Avro, RC, and Parquet with snappy compression. And you can see that in this case, Parquet performs, compared to the other compressed formats, somewhere between 40 to 100% less on disk space. So this is one of the first benefits. Now that we have arranged by column, we can have better compression. The last column on the right, I know the text might be a little hard to read, is sequence with gzip compression. And you can see that Parquet with snappy performs about the same. And this is good, because gzip is a much better compression algorithm, but much higher CPU overhead to process. So in this case, we get all of the benefits of reduced on-disk footprint without paying any of the CPU cost. Here is another chart where I'm looking at query performance for that same table. So in this case, I've authored the queries to project more and more of the columns in the original table. So the table has 16 columns, and the first set of bars on the left is if I select one column, then 3, then 5, and then the fourth set of columns in the middle is where I select the entire table. So Parquet is the last column on the right in light blue, and you can see that the cost of scanning more columns increases relatively linearly. And this is what we expect. When we select one column, we only need to read one column's worth of data. When we select 3, we need to scan roughly 3 times as much data. And you can see that it outperforms the other formats quite significantly when we select the fewer columns, as expected in our use case. It's interesting to note that even when we select the entire data set, it still outperforms the other formats by, say, 40 to 100%. And this is because we have more efficient encodings, and again, the on-disk footprint is smaller. If we move to the last 2 set of columns, in this case, I'm benchmarking the TPCH Q1 query. So this query selects 7 of the columns and does an aggregation. And you can see how performance on Parquet differs from the other formats. I think what's particularly interesting to note is the last set of columns, where we're running the TPCH Q1 query, and that is a metric for the number of bytes read in order to service the query. And you can see that for the other formats, they essentially have to read the entire data set, but for Parquet, we're reading a tiny fraction of the data. So this is exactly the goal that we are trying to achieve. So in addition to support in Impala and Pig, we knew it was very important that we have good support in Hive as well. So one of the key goals here is that we have a storage format that has first-class support across the various processing frameworks in Hadoop. To help us do this, we've been collaborating with a company called Criteo, which is based out of Paris. A little bit about their use case. So they are a personalized web targeting company. They have about 20 billion events of data ingest per day. Their schema on this particular table is 60 columns with some nesting. And their typical use cases do heavy analytics, and currently they use Hive to do this. So this combination is very well suited for Hadoop, but they would like to move to a columnar store to get better performance for their workload and reduce on-disk size. So they have been working on the Hive SerDes, which is currently in a branch in the Parquet repo. So from their point of view, here are what they needed from Parquet. So they're already heavily invested in Hive and MapReduce, so they certainly want compatibility there. They want to make sure that the Parquet files can support their schema, which varies and changes over time. And they want to make sure that the file format they choose for their data, while currently Hive is their primary use case, they want, again, to be able to make sure that in the future, if their workloads evolve, that the files can be read very efficiently in the other processing frameworks as well. So here are some very preliminary user experience numbers based on the Hive SerDes that they have been working on. So one thing to note is that the development of the Hive SerDes was done against Hive 10, but ORC and RC file are running against Hive 11. So they're in the process of porting that to Hive 11. The top set of numbers, the first row, is CPU time across 5 different queries. So ORC file is brown, Parquet is blue, and RC file is orange. And you can see that how the performance varies across the different queries. And in the second row is the number of bytes read to service that query, similar to the charts I showed for Impala. And you can see how that changes. Again, these numbers are very preliminary, and there's still a little bit of work to be done here. So with that, I'm going to hand it off back to Julian.
Thank you. So now I'm going to talk about some of Twitter's initial results. So we converted one of our big data sets, which is similar to an access log. So it's logging every HTTP request to our front end. So you have columns like the URL, the IP address of the client, etc. And it has 30 columns. And so the original format was a Swift binary in block compressed files using LZO for compression. And we converted it to Parquet. And so if we look at the first graph on the left, the blue is the original format using Swift in row-oriented storage. And you can see that converting to Parquet using the same compression algorithm, we save 20% of the space. So just that the columnar layout, improving the compression by putting together the data of the same type, of the same sort that compresses better. And on the scan time, so you have the baseline, which is blue, which is flat, because in row-oriented format, you need to read all the data independently of what columns you access. And in columnar format, so we measured for the base case scenario when we read only one column. In that case, it takes only 10% of the original time to scan one column and query on one column. And if you read all the columns, which is all the 30 we have in this data set, then it takes a slight overhead of 14% to read the data. And here there's an overhead of reconstructing the record, because instead of having right away the rows, we need to reconstruct it from the columns. And so that was with plain encoding, so columnar layout using a simple encoding for the data. And since then, we implemented dictionary encoding. So for the columns that have small cardinality, a small number of distinct values, relatively small, we can build a dictionary of those values and encode them using the dictionary instead of repeating the values. And in that case, we can compress much better. So I focused those two graphs on only those 13 columns out of 30 that are suitable to dictionary encoding. So originally, in the uncompressed data, they represent 27% of the space. But after compression, they represent only 3% of the space, because those columns have few distinct values, and meaning like from a few to several thousands or tens of thousands. And so they compress much better than a regular column with a random ID in it, for example. And so we can see that from the compression point of view, even the dictionary encoding, without applying LZO compression to it, performs better than just compression. And if we apply compression on top of it, then we fall down by a factor of 2. It's only 50% of the original space. And so that's applying to Parquet. That's applied on top of the savings we were talking about on the previous slides. And in scan time, you can see from the graph here that we have similarly 48%, so about half the time to scan those 13 columns compared to the time it was taking when they were not dictionary encoded. So it's potentially a very big win for data sets that have a lot of strings that are repeated. And now I'm going to talk a little bit more details about the format. So as we talked about, it's a columnar format, so the data is organized in row groups. A row group is a group of rows organized in columnar format. A column chunk is the data for one column inside a row group, and a column chunk is made of pages. And so the idea is when you write the data, you're receiving one row at a time, the rows being written, and you need to buffer the row group in memory so that you can write it in columnar format, one column at a time, because you need all the data for the first column before you write it out. So that's why it's organized in row groups. And so a row group should be about between 50 megabytes to 1 gigabyte of size, roughly. The idea is you can adjust that as a setting depending on what budget you want to give to this when you're writing, because that would be part of a job that is doing a query or something else. So you want to be able to limit how much memory it's going to use for the columnar storage. But potentially, the bigger it is, the better performance you will get from optimizing the scans when you scan only the columns you need when you're reading. The page is a unit of access, which means the bigger the page, but that's also how we compress data. So the bigger the page, the better compression you're going to get. But also, the bigger amount of, the most data you need to decompress to access a single value. So that's to give you an idea of the different things in the file. And so here's a more visual representation of the file. So you can see it's a sequence of row groups, each row groups containing column chunks. And at the bottom of the file, you have a footer containing the metadata for the file, including the schema and other things, and also the pointers to all the column chunks in the file. So that's how we read the data to improve scans. So the splits are based on the footer data, so we know exactly which column chunk to scan in the file to read only the data that we need. And this is all language independent. It's formally defined, and both Impala in C and generated code implements it, as well as Java code in the Parquet MR repository. So I started by explaining to you how we have a deeply nested data structures and how we represent them in flat columnar format. So there's a missing piece here, which is how we capture the structure of the record in the columnar format. So we use the algorithm that is described in the Google Dremel paper. So I invite you to go read that paper to have more information. I won't have time to explain in details how that works, but I will give you some information on why it is efficient. So we don't store only the value in each column. We store a triplet, the value plus 2 integers, which are the repetition level and the definition level. And the definition level and repetition level will capture the structure of the record. So there's one column per primitive type, which are, if you represent the schema as a tree, which are the leaves of that tree. And the definition level capture whether the field is defined or not, whether it's null or not. So if the field is defined, the definition level is equal to the depth of the tree at that point. If it's not defined, it's going equal to the node where it's not null, the first one. And the repetition level will capture in what field, in what node in that tree there was a repetition last. So it will capture the structure of the lists if you have lists adding the repetition level and definition level. So those are two different ways of storing the nesting, but both would be equivalent in how it stores. So we have two APIs to access this data. The first one is the one to integrate with Hive or Pig of MapReduce, which are row-oriented execution engine. So it knows how to assemble any subset of the columns. So the idea is you can tell it which fields in your schema you're actually accessing, and you'll be able to reconstruct the records populating only those fields, which means we're going to be able to have efficient scan, but scanning only the columns you need, and it's going to reconstruct the record with only those fields populated. And it's built on top of the column-based API, and this column API lets you iterate on those triplets. And this API is designed more for column-based engines, and it will allow to optimize filters like you can imagine if you have an expression, if you have a filter on some data, and you want to filter on A equal 1 or B equal 2, the row-based execution is you read both columns and you evaluate the expression and you decide if you keep the row or not. And the columnar evaluation, you would evaluate the expression on A first, on all the column A, and then in the column B, you can read only the record that satisfy the expression for A and A equal 1 and B equal 2. So if A is not equal to 1, you don't even need to evaluate on B. So you can do this type of optimization. So again, the idea is to provide a framework that can work for any of the tools that exist. Like Hadoop doesn't have any notion of schema, but there are plenty of tools that have a notion of schema, naming Pig, Hive, Avro, and others in the Hadoop ecosystem. And they all define schemas in a different way. So the goal was to have an API that really allows to convert from any of those schema definition and any of these object models, and removing any overhead of double conversion, right? We avoided having an object model that would convert to and then would be converted to the Pig tuples, for example. So we built an event-based API similar to Stacks that will send like add attribute, add value, add field, add value, and field, and that lets you materialize those records. And we already have integration for Impala, Pig, Thrift, or Scrooge for MR and cascading and scalding, and cascading tuples, Havro, and Hive integration. So this API lets easily materialize the object model for each of those tools. And now I'll let Nong talk about the encodings.
Thanks. Yeah, so Julian has been talking about the high-level structure, right? We have row groups that are split into column chunks. Each column chunk is divided into pages, and pages are the unit of processing. So each page has its own encoding, and the encoding has a huge impact on both the on-disk size as well as how quickly we can read from that page. So we have what we call the default encoding, which essentially is the most efficient to decode, the machine architecture, little Indian encoded value. And on top of that, we have 3 currently encodings that can be used instead of that. So the first is bit packing, and this is well suited for columns that have values with low max values. So a small bit width can be used to represent the value. An example of these columns would be the definition and repetition levels that Julian talked about, also for bools or enums, where you know that there's only a handful of possible values to start with. And in this case, this is very similar to the encoding used in Dremel, where we essentially take the bit width, say in this case 3, and if we encoded 3 values, they would just be stuck back to back. So in this case, they would fit in 2 bytes. So that's the first one. The second one we have built on top of bitpack encoding is our custom run length encoding. So this would be used for the same type of data as bitpacking, so small bit width values, except here we're able to take advantage of runs that exist in the data set. So here's an example where we have a run of 8 ones, and it gets encoded to 2 bytes, an 8 and a 1. Our run length encoding is fairly sophisticated and knows how to switch back and forth between these runs and what we call literal groups, where things don't repeat. So if you had a string of 1s and then alternating 1s and 0s, and then a string of 0s, it would know how to switch back and forth. And we compute sort of the break-even point when one encoding is preferred over the other. And the sort of metadata associated to figure out if you're in a run or a literal group is very low. So we sort of get the benefit, the best of both worlds. And thirdly, we've added dictionary encoding for string columns with low cardinality. So in this case, we have a fixed size dictionary, and if your column has low enough cardinality, then we just encode the values as indices into the dictionary, and the indices themselves are encoded using run length encoding. All of this is extensible. So these are the encodings that we have built first, sort of the biggest pain points and things that gave us the biggest bang for the buck. But it's simply an enum, and we plan to add more encodings in the future. So this time I'd like to, aside from Julian and myself, there have been quite a lot of people who have been worked on this at Twitter, Cloudera, Criteo, and elsewhere. And we're very pleased that at this early stage, we sort of have a bunch of external contributions who have helped us either with the format or the implementation or integration into other processing frameworks. So I highly encourage you guys to give this a shot. If your framework of choice is not supported, we'd love to get it added. And then the future work. So we're getting close to what we want to call the Parquet 1.0 release, where we are going to support all the things that we talked about in the previous slides. But we're already started to look forward and take advantage of some of the extension points that have been built into the format from the beginning. So we have currently what we have these pages, and they have different types. So we've mostly been talking about data pages that actually store the values, but we have plans to add index pages to essentially give us single row lookup by inserting that periodically through the file. I already mentioned more sophisticated encodings. These could be delta encoding or delta run length encoding or group encoding for integers with small values. And then other page types would include things like stat pages, where we could keep a track of the histogram of the data in the file and things like that. And all of these are natural extension points from the format specification. So I think that is all we had prepared. At this point, we'd like to take questions, if there are any.
We have one contestant on the right.
I think
We have one contestant.
Oh, I think there. Please just go to the mic. I think that's how it's being done. Yes.
Hi, thanks for the talk. I have two questions that are somewhat related. I've looked at Parquet a couple weeks ago, and I had not found any Surday for Hive. Has that support been added very recently, or?
So the Surday, sorry, you forgot to mention, the Surday is in a branch. So it's going to be merged pretty soon, but it's still in a branch, and you can see there's a pull request. So if you go on the GitHub, there's a pull request with the Surday in it, and we're in the final. It's a pretty big batch, and we're in the final rounds of reviews, and it's pretty close to being merged.
Awesome. And the second question, if I'm not mistaken, I think Impala does not currently support nested structures. And I was wondering if the Hive Surday does support nested structures with Parquet?
You're correct. Impala currently does not support nested structures. It's something that we are working on. The Hive Surday does.
Awesome. Thanks.
Welcome.
Hi. I have a question about dictionary encoding. You mentioned a limit of around 50,000 different values as the sweet spot for dictionary encoding. Doesn't that also actually depend on the length of the values?
Yeah, that's correct. So we have two settings. Actually, this limitation to 50,000 is not a hard limitation, but at some point you want to limit the size of your dictionary. So there's also another limit, which is a setting that limits the size of the dictionary. But basically, it's something you can tweak. You can say, you can change the maximum size you want to allow for the dictionary. And knowing that the bigger the dictionary, the more memory you're going to use when writing or reading. And these kind of things to take into account.
Okay, so basically you can just say, I accept that my dictionary occupies so many megabytes in RAM when reading or writing, and...
Yes, you can do that.
Okay, thanks.
You're welcome.
Yep.
Hello. So question, given that we already have HBase and Cassandra, and they're both pretty mature, what made you decide to write your own columnar data store?
So I think the two examples you gave are not quite analogous. I mean, this is a persistent sort of read-only file format that's really optimized for scans. So HBase has a backing H file, but that's not something you're expected to sort of read directly, right? You want to go through HBase to access the rows. So I think because of that, the goals are a little bit different, right? We want a format that is for your historical archive, like historical data, that's not going to change, and we want the absolute best analytic performance on that data set. So I think those goals are a little bit different than some of the other frameworks we've talked about.
So it's read-only is what you're saying?
Yeah.
Yeah, I mean, it's read-only.
It's a file format for HDFS. So it's not, there's no service on top of it. I mean, it's HDFS.
Got it.
Yeah. And in HBase, for example, because it's a updatable data store, the cost of reconstructing the state can be pretty high depending on the case. If you had many updates, you have multiple. On read, it's going to merge multiple files together, so you have that extra cost on top compared to a file where you just scan the columns you need.
Could you talk through the pros and cons of creating an entirely new format versus extending RC file?
You want to talk about that?
Sure, I'll give it a shot. Yeah, so I think, I'm not sure at what point you're creating an entirely new format versus extending one. I think that when the differences are so big that there's no way an existing scanner could possibly read it, right? Whether you call this RC 2.0 or a new name it really doesn't matter. There's no legacy support, no existing scanners are going to work. So I think there are some pretty big differences between the RC file as I understand it and what we have spec'd for Parquet. So in particular, the support for complex types is very different. RC file, as far as I understand, uses a lot of text-based encodings, which Parquet doesn't. The structure of the file looks very different. Right? We have these row groups and the metadata at the end, and I think RC file sort of has some of that intermixed throughout the entire file structure. So I think these differences are sort of fundamentally incompatible, so I don't really even know what extending it would have meant for us.
Yeah. So if we want to extend something, it has to be extensible. So in particular for Parquet, we pay a lot of attention to define the metadata in a way that it's easy to extend. So all the metadata parts in the file are defined using Thrift, and we have the notion of encodings and compression algorithms, and so it's easy to extend to add more encodings, adding more page formats. So you have a notion of page, and you have a notion of page type, and the metadata is version. So we spend a lot of time making sure this format is also extensible, is easily to evolve in a compatible way that not all formats necessarily allow easily. Yeah.
So I noticed that you obtained performance numbers with Snappy in some cases and with LZO with the others. Did you use LZO for these other runs as well and see how it compared?
So some of the performance number we showed were benchmarked using TPCH, and some were actual real-world files that were converted. So at Twitter, for example, we use LZO. So we used LZO as well, and it's just measuring the actual changing we have. So that's why we use LZO. I think for the Impala benchmark, you used Snappy.
Yeah, we just find that with our customers, Snappy tends to be the most popular, so that's the one we benchmark. I just want to point out that within a single benchmark, we were consistent with the compression codec, right? So it wasn't apples to oranges, we were picking the same codec. In my experience, LZO and Snappy perform pretty comparably, so that's...
So have you used LZ4 at all?
I have not. I've heard good things, though.
I see. And you mentioned these other compression primitives like run length encoding and bit packing and so on. Some of them are integrated into the high-level compression formats like zlib or gzip and so on. So, so have you checked out the effect of those high-level formats?
To some extent. I think we benefit a little bit more because when we do run length encoding or bitpack, we have a lot more specific knowledge, right? In our case, we know the max bit width, or it's not even the max, the fixed bit width. And this allows us to do optimizations that I think a general compression library could not, right? We've sort of done some benchmarks, very targeted micro benchmarks on how many values can we extract per second using some of these encodings. And they're much higher than what you can get out of a compression codec, right? For some of these codecs, we can output 1 billion values per second using our custom stuff, and I think that's right. Sort of the general compression libraries, they might get the same on-disk compression, but the decoding, right, they have to solve a much more general and difficult problem.
Hey, so you've mentioned the fact that you've got plans for other future encodings for columns, and also the fact that, obviously there's different returns on using RLE versus dictionaries depending on the cardinality of the column, basically. Is there an easy way right now to rebuild a single column if you want to kind of benchmark without recreating your whole table?
So right now, we don't, all the columns are stored, so we have one file.
It's within a page, yeah, right.
So each, a single page has data for only one column, right? Pages are per column.
Okay.
But the row group would have all the columns. So right now, we don't have a way to store a column on the side, like to rewrite only a single column. Probably in the future, we'll have support for that, but right now, you would have to rewrite the whole file, yeah.
Oh, okay, so it's going to be pretty painful in the future if you develop a fairly large table and you want to change one column to a new encoding. It's going to be like a decent task to
well, if you do it in MapReduce, it's a map-only job that would read one file and rewrite it. So it's relatively fast because it's pretty easy to parallel. Yeah, it's really parallel to convert that. But yeah, you have to store the data twice in that case if you want to experiment with that. Yeah, usually what we have to do is we experiment on smaller size, like only 1 hour of data, for example. And then you apply it to the whole data set. But yeah, that's a big data problem. It's like it's hard to store it twice.
Yeah.
Yeah.
All right, thanks.
You're welcome.
Hi. How far have you rolled this format out within Twitter? I mean, and what percentage of your files in HDFS are now in this format?
So we have converted our biggest log category, which is the one I talked about, and it's several. So we saved 28% of this category, which is about 6% of our cluster, 8% of our cluster, I think. And I'm sorry, I'm trying to not give specific numbers. And so that would be saving saving 1/3 of 8%, and we're saving 3% of the cluster. And at the size of our cluster, it's pretty big. That's a lot of data because the cluster is always big. We have the log categories, which is the raw data that we're processing. Then you have a lot of derived data set that use space as well. And a lot of teams using all that and competing for space. So it's a big deal to save 3% on the cluster. And that's a start, right? We're planning to convert more of our big data sets.
Hi, I was wondering if you could speak to how you decided on which data types you wanted to support. I don't think you covered it in the talk, but I was looking at your GitHub project.
Yeah, so some of them, so the data types, I think we try to keep it relatively small. And so we have like ints, floats, and like ints of 32 bits, 64 bits, floats, doubles, byte arrays. And the goal being that we want to define a serialization format, and it's not a high-level schema system. So it doesn't have maps, it doesn't have lists. It can store repeated fields, but it doesn't have like sets. Like Swift, for example, knows lists, has lists, sets, and different things. So we're trying to make the smallest denominator of the types that we need. That said, we're adding some types based on what Hive has. Like, for example, there's a 96-bit timestamp thing in Hive, so we're going to add that. But we're trying to keep those types small to something that we're going to still be able to have efficiently encoded, but without having a profusion of types that are more semantic than actually a serialization format, if that makes sense.
Yeah, we tried to pick the set that was sort of necessary and sufficient. So for example, one thing is we don't have 16-bit ints, we just have 32-bit ints. But we believe that a 32-bit int with the right integer encoding essentially gets you a 16-bit int on disk. So you don't really pay any storage but having fewer types in the file format means if you're implementing it, you have less work to do. So that's sort of how we came about thinking about it. If we took the type and the best encoding we know how to do it, if that gets us all the benefit, then let's throw out these other types that we don't need.
I guess notably, I saw a lack of a decimal support. So
Yes, so we have a fixed byte type, or fixed byte length type.
Yeah.
But maybe we can talk about that offline.
Yeah.
Hello, and my question is, how long does it take to convert to Parquet format in Twitter scale, at Twitter scale? So I think conversion is needed, and at first the data is saved as JSON format or something, and conversion is needed.
Yes. So we already had a conversion step. So the data comes, so obviously instrumentation data comes one row at a time, right? It comes from events from the front end that there's instrumentation that send events, and events get consolidated and returned to HDFS. So we already had a step that was consolidating those events and storing them in a more efficient format, because the log file obviously are more like line delimited, because it writes one event at a time in appending, so it's more line delimited. And we already had something that was writing to Swift block compressed files. So we replaced that step. So it's not like converting to Parquet didn't become an extra step on top of the pipeline. It replaced the existing consolidation step that was putting a lot of small files together in bigger files that were better compressed. So it takes...
How is the latency, for example, in Twitter?
So the latency, I think we have something like, yeah, it's in order of tens of minutes. Because one thing we do is we want to compress that data. So again, one important thing is to save space on the cluster. So we use LZO, and LZO in particular, you can adjust compression, and you can tell it to compress more, and it's going to spend more time compressing. And the good thing is it's not going to take more time decompressing, right? You have a negligible overhead on the read time, but you take more time writing. And most of the time you write once, and we read many times. So we took this approach to save space on the cluster. So we have a certain amount of latency on that side, but we will use other tools that have lower latency, more streaming like Storm and things like that to do real-time analysis. So the analysis on the cluster usually, yeah, some latency. We add partition 1 hour at a time. So you always have at least 1 hour of latency, because what happened, you know, we add data only 1 hour at a time on the cluster.
Okay, thank you very much.
You're welcome.
I think we're running over time.
Oh, is that positive now?
Yeah. So I guess we'll be at the booths, so if you have questions that you didn't get a chance to ask, please.
Booth 26 and
Just find
45. Well,
Thank you.
if nobody kicks us out, let's see.